So now we're going to consider the moving observer, okay? So Mindolator is holding a clock, okay? He's like Flava Flav. He's got a big clock. He likes to watch it. That's all. I mean, sitting in a spaceship by himself in the middle of space, what else is he going to do? So he's got the Flava Flav clock, and he's just watching it. Well, then, you know, somebody else has a big clock too, and they're holding it out the window as they drive by, and they're like, look at my clock as they drive by, right? And so Mindolator looks out his window, and he can see the clock moving through space. So now we're going to have two clocks. All right, so then we know that there's we can write some velocity that the Mindolator's our friend who's trying to show him the clock is writing, and we'll write it the following way, right? It might be a little bit weird, but the friend is going to be moving in a frame of reference, so he's going to have a different coordinate system, okay? He's going to have a different inertial coordinate system. We just talked about that, like rotating into that and how it'd be a different coordinate system, and that manifests itself as a velocity, and that's going to be equal to velocity of dt, like that, right? Which, I mean, you guys can see this is just dx over dt is equal to v, right? The velocity is equal to dx over dt, okay? Now, so this is what observer 2 sees. Observer 2 sees dt squared, which is equal to, not squared, prime. Prime, yeah, prime. Okay, so now he sees this d tau prime. And what is going on with that? Well, that's going to equal dt prime squared minus our 3 vector squared, which 2 of the components are going to be 0 because he's only moving in one direction. So it's really just going to be the one component of x. And that's going to be equal to delta tau. Okay, so a new delta tau. Oh, no, excuse me. I read the wrong part of the notes. That's going to be equal to what? Well, we have dt prime here, so it's going to be 1. We're going to pull that out. And then we also have a v squared from here, because we're going to x squared is going to equal v times dt squared. So when we square this, we're going to square this, and then we're going to pull out the dt prime. Okay? So we have a new coordinate system. But we know that under any Lorentz transformation, d tau prime has to be equal to d tau. What does that mean? Well, d tau is equal to, that means d tau is equal to delta t. And d tau prime is equal to 1 minus v squared over 1/2 dt prime. So that means that dt prime has to equal delta t divided by the square root of 1 minus v squared, which equals gamma delta t. So this new time coordinate, basically, as Mindolator looks at the other observer's clock, it's not going to be ticking at just delta t. No. It's not ticking at 1 second per second anymore. Now it's ticking at a new time. It is no longer 1 second per second, depending on how fast it goes. And like I said, if you want to actually do this, you can look up the Lorentz factor, which I think is v squared over c squared. Someone correct me if I'm wrong, but I think the correct, if you don't set it to equal to 1, it's 1 over the square root of 1 minus v over c squared. They're both squared. And so if you want to do like what the actual calculations would be, you can start plugging in some numbers. You could do like 0.1 the speed of light or something like that. My perspective only though, yes, from your reference frame only. Looking at his clock, it's going to do that. And then he could look back at your clock and do the same thing. Very interesting stuff to think about.